Okay, so thanks everybody again for joining us for day 2 or day 3, I guess, depending on where you start counting. I usually start counting from the beginning of the week. So, but yeah, well, I guess if you came to the prep day, this is now day 3. So for this next session, we are, second to last session of the day on high throughput computing. So I'll be talking about this topic. This is like the last 2 days. I think Bob mentioned originally from the first session that these first 2 days are sort of a lot of new material that we're putting together. So like my talk yesterday on data management, it's still sort of evolving and probably not quite fleshed out completely, but I do again have sort of this new format using the markdown in the GitHub repo for you to follow along with me as we sort of walk through some exercises on this topic for high throughput computing. So I think Cindy already pasted the link, but I'll paste it again just to point it out. So if you want to follow along with me as we walk through this, you should be able to copy and paste from your web browser into your terminal. So let me get a terminal set up for myself. I'm going to close the Slack, but hopefully I'll catch any pop-up questions that come. But Cindy or anything else, the staff, if there's a good question to stop on, please just let me know. So I'm just going to get this set up now. Make this a little bit more visible maybe than it was yesterday, with increasing the font size in the browser too. So if you go to the high throughput computing section in the Summer Institute repo, this is where we'll begin. And so I'll start the talk now, essentially. So what is high throughput computing? So high throughput computing is involves generally running large workflows of many small jobs. You might want to do this when you have some code that you want to run over, say the same simulation many times, but over slightly different parameters in each simulation, or slightly different input files. Maybe you're processing lots of similar data files. You just need to run, say, on a single core over 1 million files. Like, how do you set that up on a system like Expanse or any HPC system? That's really what this talk is about. And so because there's caveats when you're trying to do these high throughput computing workflows, and they can cause problems on most HPC systems, even though they're pretty popular with a lot of people. A lot of people's work don't need these large parallel MPI jobs to do their science or engineering or whatever your research involves. You might just need many number of jobs, small jobs run over a great amount of time to get your work done. And so that's what we're going to talk about today, like some of the nuts and bolts practicalities of starting to understand some of the tooling you have available on a system like Expanse or any HPC system to start building these high throughput computing workflows in a safe and effective way for your research, but also, again, as we talked about yesterday, as being a good neighbor and fellow researcher using a shared system like Expanse, right? So there's ways you could do these things that would cause lots of problems for people, but you want to try to do it efficient and performant for you, but also using the system correctly. So like yesterday with the data management talk, I have a few different sections here. We'll try to get through as much as we can. I have about, well, now a little less than an hour to talk, I believe. We're going to, yes, 1:45, or no, sorry, 12:45. Sorry, I'm on the East Coast, so the time on my laptop is different from the actual time, so I get a little confused sometimes what time zone I'm in. So the first section here is the parallel paradigm. So if you want to click on that, I'll just talk briefly about how HPC is different from HTC, high throughput computing. So of course, when we talk about any sort of computational problem, right, you start off thinking about your problem in sort of a serial fashion. You have some serial problem that you break up into a set of instructions. You send that off to your CPU to get each instruction processed, and it takes, each set of instructions takes some amount of time, right? As Bob talked about, I think, for the first day, this idea of Amdahl's law, right? Your performance is always going to be limited by your serial computation. So, when you want to speed things up, you can break your problem up into multiple sets of instructions and submit them to different independent, CPUs, but you're always going to be limited by some chunk of instructions that's running in serial, right? So the difference between high performance computing and high throughput computing is you're still going to try to parallelize your problem. You're still going to break it up into a series of instructions and send them off to multiple processors. The difference really is there any communication between those sets of instructions, right? When you're talking about MPI-based codes, where you're passing messages between instructions in this pipeline, that's what we call sort of these tightly coupled codes, where you have to exchange data between sets of instructions. And that's where MPI and OpenMP and these other parallel programming frameworks that you'll use to communicate data between processors and between instructions as you try to solve your problem in parallel, right? That's sort of this one way to think about parallel computation, right? However, in the high throughput computing world, what you're usually doing is these instructions are completely independent from each other, right? So you just want to run, say, one single core job over many files, same set of instructions. So you can really just send those jobs and that piece of the problem, off to many independent processors and not worry about any sort of communication with one another, right? All you really want is lots of cores processing lots of, say, individual files or pieces of data that you need to get done. So that's sort of the difference. And this is kind of illustrated here by these sort of three ways of thinking about why would anyone go parallel when you're trying to do a computational problem, right? So, one of them is speed, right? This is this traditional high performance computing type of way. You want to solve a problem more quickly, as fast as possible. For example, if you have a hurricane coming towards the United States and you want to try to predict where that hurricane is going to land, you need to run a couple simulations every day, every couple hours for a day to get updates on the hurricane. So you might not be able to really know all the sort of intricate details of this weather pattern that you want to try to predict where it's going, but you just need to solve something very fast and as quickly as possible, right? This is where you would use these, large, ocean weather simulation type models, with definitely using MPI and OpenMP and all these fancy parallel frameworks that you would use, right? Of course, you can then, if you're not too concerned about speed, you might just be concerned about higher fidelity, more complex physics in your model, right? So again, this is actually the same problem solving for a hurricane coming towards the United States, but in this case, it was actually, if you look at the links here later, it's comparing what the simulation capabilities were in 2005 versus 2015, about sort of the same, using the same model, but it's just 10 years later, the resolution and the fidelity and the physics that's in the model 10 years later was just much more complex with this sort of higher fidelity. So you can get sort of a higher scale or resolution to the problem you're trying to solve. And again, this is another traditional way of using the HPC model, right, where you want to solve a more complex problem. And then that's where we get to the throughput, back to the HTC problem. It's really about solving many, usually simple problems more quickly, right? And one really big experiment out there that uses high throughput computing is this IceCube experiment at the South Pole, where they're trying to detect these particles from astrophysical sources in this sort of kilometer square block of ice with all these different light sensors. These little balls here that are lighting up are these light sensors picking up information about the particles that have passed through the ice down there. And what they do is they do a lot of simulations of these events that happen in the ice to understand, what they see from the detectors, these flashes of light that they detect in this block of ice. They run lots of simulations to understand what type of particle hit the ice and what that sort of what they call a shower would look like, right? In the ice and in their detector. And so what they want to do is run many versions of these simulations of these particles hitting the ice, so they can filter out which ones or understand which ones happen more often, or which ones are give a certain type of pattern, and so on, right? So they just need to solve a lot of these different simulations with slightly different inputs, right? Because it's always the same problem that they're trying to solve. It's just slightly different inputs, and at the end they need to try to predict what the flashes of light look like in the ice to get back to what the particles they detected were, to understand what the particles are. And so there's some nice SDSC articles here you can read later on, but one of the, this is all the reason I chose this one is it's one of the extreme examples of where they had this large experiment called a cloudburst experiment, where they were able to actually gather more than 50,000 GPUs across, I think, Amazon Web Services, Microsoft Cloud, all the cloud providers. They were able to sort of, for 2 hours, sort of try to gather as many GPUs as possible and run these simulations. So they got up to sort of 50,000 at the peak or so, to just run a bunch of these simulations and improve the accuracy of their predictions of what sort of the modeling of the light going through the ice was. And so they were able to sort of, I think if you read the article, improve like their sort of error bars at like sort of a factor of 4, just by having more simulations, understanding what the outcomes should be in their detector. Okay. So that's high throughput computing versus HPC, right? So we want to solve many problems, right? So we're going to solve a few problems today with the examples that I have. But just kind of give you some of the tooling that you would use on a system like Expanse, specifically for Slurm. We'll talk about batch job arrays, batch job dependencies. I think we'll get to job bundling. Maybe just touch on it a bit. It's not my favorite topic because I prefer people use job arrays if they can. It'll probably make sense why. It just gets more complicated when you do that, but it's definitely another technique that's used in this sort of in this problem space. But what we're going to start with is batch job arrays. And if you haven't noticed, all of the other topics, except for all these topics where we actually have sort of examples, I put batch in there specifically, not just to be redundant, but just to remind you that this is really about running batch jobs, right? So if you're doing high throughput computing work, you're going to be wanting to write batch job scripts. You're not going to be doing interactive jobs. This is really to start scripting your workflows in ways that are a little bit more complicated than just a single job that you would run, that you might just be more comfortable doing interactively. This is really, if you have lots of jobs that you need to run, you need to start scripting your jobs in certain ways. And these are just some more advanced tooling that is available to you from sort of the native Slurm environment that we offer on Expanse. But this is sort of true of any sort of scheduling software you'll probably see on a HPC or even HTC system out there, right? So there's these ideas of job arrays, job dependencies, job bundling. You can take them anywhere you want to go. These specific examples are just for Slurm and just for Expanse, but the concept should be transferable to your campus cluster or another, say, Exceed resource you might be on. So we'll go ahead and get started. So I'm going to again sort of try to walk you through some of these examples. If we get hung up and start running out of time, we have about 45 minutes left. I might speed up or skip some, so you can always come back here. Again, this is sort of an evolving training document at this point, but you know, I think it touches on a lot of the things that you should at least be aware of if this is your type of problem and you're not familiar with some of these concepts. Okay, so I'm going to log into my training account. So you can, if you're following along, go ahead and log into your training account. And what we're going to do is we're going to set up an example problem. So I have this repo here that you can copy the git clone command. I'm going to clone that repo to my home directory on Expanse. Now, this project is just a simple collection of programs that estimate the value of pi. It's just kind of a working repo I have for these simple problems that it's easy to make examples out of. So that's kind of what I'm using it here for. So you can read sort of the description in the git log if you want, but I've sort of copied and pasted that here. But the main thing is really in this diagram. So what the programs that we'll use today, curious, it's using this sort of simple Monte Carlo method to estimate the value of pi. So the idea is essentially you have a box and you have a circle. You pick random numbers between, you know, the area of the box, and the ones that fall outside that circle, right, are counted as outside. The ones that fall inside the circle are inside. And if you actually just do a little of the math here, you can estimate the value of pi just by counting the number that are inside and outside the circle, right? And times multiplied by 4 here. So that's all this program is doing. The programs that we're doing, it's just we have a few different versions in here. If you look at the repo, change directories, you'll see there's a bash version, a C version, a Fortran version. Actually, I don't think I have the C version yet, but there's Python version. So we're going to use some of these programs just to set up these and explore job arrays, job dependencies, and job bundling today. Okay. So you can, if you're familiar with the languages, you can play around with them yourselves. But what we're going to do is I do have some batch job scripts that I've sort of pre-scripted for us. We'll be making modifications to them. So the next thing you need to do, besides cloning the repository, is downloading this estimate pi shell script. So I'm going to go back to my home directory and just wget that estimate pi from this command. Right, so you might have more files in your home directory. I cleaned mine out before I started just to make this a little bit easier for people to read and follow along. So I should have at least that 4pi repo and the estimate pi shell script or batch job script here. What I'm going to do is open up that batch job script and just take a look at it so we can see it here. I think I've copied and pasted it here as well. So if you want to just use, if you're not familiar with VI or Emacs yet, you can just use cat to sort of echo the contents of the file back to your terminal. But I've opened it up with VI, my preferred sort of text editor, just to give it a little bit more color. So again, this is just a standard batch job script. You have your shebang line, then you have your commands or your options for Slurm. You see there's a few extra things in here today. Again, we're using account CRL 155 for the rest of the week. We will have reservations available, but they'll be daily. So if you see an error in a script when you're trying to run it, this is definitely one to check if the day hasn't been updated, or the instructor might be missing something in the typo. We do have these reservations. Again, you won't have access to these reservations after I think sometime today. So this script might stop working if you try to run it later. So you'll just need to take out that reservation line, but you should still be able to run it. You'll just have to wait in line with the rest of the users on the system. Okay, so it's very simple, right? We're just going to run in the shared partition, right? This is again the partition where you can have multiple user jobs running on the same compute node. We have 128 cores on every compute node. So this is going to run on a single node. We're going to have one task per node, one CPU per task. So single core job with 1 GB of memory. And I just set the time for 30 minutes here because it doesn't really matter too much for what we're doing today. So basically, what we're going to do first is run this bash pi version of the program. And it has 3 inputs. It has this -b, -r, and -s. If you want to look at the code, I put this command here. If you want to copy and paste this and just run that on your command line, it'll just output the first 15 lines of code on the command line. Right, so you can look at it like this. It's not too interesting, but basically, it just gives you an idea of what these inputs to the code are, right? So we have bytes, round, and sample. So basically, there's a variable that you could set to set the number of bytes, sort of how I think it's for the integers that I use in the code, how many decimals I round my estimate of pi to, and then the number of samples. So how many darts I throw at that board to try to figure out how many fall inside and outside, inside the circle and outside the circle. Right? So that's what the -s is. And if you're curious, this time p command out in front of the script is just to give us an estimate of the runtime of the command for the job. So, okay. So I think that's all I wanted to cover there. And so what you can do if you have your estimate pi, it should be set, ready to go. You should be able to just sbatch and submit the job to the scheduler. All right. You can check that the job's running. I've set up most of the examples. They should take roughly a minute max to finish the job. So I'll probably keep talking as things run, and then we'll check back here when we get the outputs. So I'm going to scroll down. But yeah, most of the examples, they should run in about a minute is kind of what we've set up. I'll try to remember when they don't, but in general, they should take about a minute. So what we'll do when the job ends, we can check the standard output file for the results. So we should get back a standard output file. My formatting of output files is a little different. I just put a .o, the job number, then the name of the node at the end. Another thing to note when you're walking through these exercises, I try to be somewhat careful of when I put a text box like this with stuff that's output from my terminal. Obviously, the job number here and the node name here have changed since I ran it while compiling the documents. So it's not. I try to make it not just straightforward copy and paste like some of the other commands that you can just run as is. So you'll just want to try to run it by hand yourself, right? So if I go back here, looks like our job is done. I have an output file, so I can do cat estimate pi -o, and I get a similar looking output. It looks like it ran a little bit slower. When you're running in the shared partition, you're running with other people on the same system, so maybe there was some churn on the node that I landed on. Maybe yours ran faster. This is one thing to keep in mind when you're running on shared nodes. Okay, so if you have that job, that's our sample job to start with. So what we're going to build on from here on out is this estimate pi shell script. So the first thing we're going to do is talk about, okay, well, what if you wanted to, this is like a very, it's a much simpler Monte Carlo problem than, say, the ice cube problem that they use for simulating particle events and high energy physics. But it's still this is a Monte Carlo program. This is a kind of a quintessential type of application that no matter how fancy it is usually you're going to run many of the same version of it, right? And so if you're doing Monte Carlo simulations and you want to run many versions of an application, many times, just because here, right, we have different random inputs, every simulation is independent and different, but it gives us another estimate of the thing that we're looking for, right? And maybe then you'll want to eventually combine those results from many of those simulations. So we're using this as our stand-in fancy Monte Carlo program. It's very simple, but what if we wanted to run, say, 10 versions of it, right? That's what this first create your first job array exercise is. So the modifications that you need to make to the batch job script are here. So I'll just copy those and then bring them over here. If you're not familiar with editing files as well on a terminal yet, it just takes some practice. I use VI, Emacs is it's kind of the other most popular Linux command line editor. We also have Nano, if you're familiar with Nano. But let me just paste in these two lines here. You can also try to just type things in if you're not familiar with all the commands yet. You'll see here, I'm going to change the job script slightly. So the two lines I'm changing are the output and adding this dash dash array. So this is how you set up a job array. And so you have this index here that you can apply, and I'm going from 0 to 9. So I'm going to run 10 versions of the same program that we just ran, right? But all I need to do is have one job script, right? Now you'll see that I'm modifying the output sbatch command here because Slurm, has this tooling around submitting job arrays where instead of just having a single sort of special character here for your output job script naming, it has two. It has a % capital A and a % lowercase a. And this stands for the Slurm array job ID, and this is the Slurm array task ID. And so you'll see here at the end that this indexing here ends up in this small a, where the capital A is just like a regular Slurm batch job ID. Okay. So I'm going to close that, and all I've changed were those two lines, and I'm going to sbatch submit it to the scheduler, check how the job is, and you can see all I had to do was set up a single job script, submit that single job script, but it's generated 10 different jobs, right? So that's kind of what, being aware of these tools, it gives you this extra special ability to start running multiple versions of the same application that you want to run, right? So again, this is going to run for, a minute or so. And what we'll see is we'll get, we should get, we had our original batch job here that we ran a single one, but we should get a bunch of output files with individual estimates of the value of pi, but you'll see that it has a job ID. This is now the array task ID or array job ID, and then there's the individual index numbers from that lowercase a, right? So you can start keeping track of which simulation is which, because not necessarily, even though the examples here are running all on the same node, they're not necessarily running on the same node, but if you run into a problem with a single task that gets, killed for some reason, as Nicole talked about, it's like, one of the things you want to reference to the help desk is not only the job ID, but maybe if it's a specific array task as well. So was there a question in the chat? Are you running the same code 10 times without any modifications to code? Yes, sort of. Right. I think my code is almost done running, and we'll see here in the results that yes, I'm running the same code 10 times without any input modification right now. However, right, this is a Monte Carlo code, so every time, if you look at the code, it's basically throwing up, throwing dice at every iteration in this loop. So every output from every instance is actually different. Right. So if it was a deterministic code that, ran exactly the same sort of weather simulation, you would hope the inputs to the, if the input physics is the same, hopefully the output physics is the same too, if you don't have, a lot of randomness built in, like we do in this code. So good question. In this case, right, it's the application is really, I just want to run a bunch of different estimates of pi, and I can, in theory, maybe combine these results to get a more accurate result. Right? So that's kind of the idea behind this this version. So this one's running a little slow, but another thing we'll do while we're working today is, I forget if someone showed it, but you can also, anytime you have a job that's running, you can also log into that node by just typing SSH in the name of the node. And then I can run the top command and look at my, just have a bunch of bash processes running. Those are the bash pi code estimates, but we have a bunch of people probably already, so we're all on the same reservation, so you can see we're all running the same code, and so it's probably causing a bit of churn, and the simulation might be taking a little bit longer. That's okay. Oops. Okay, so I've logged out of that. Okay, so good note for timing in the future, probably to decrease the simulation time. But I'll let this run and keep talking as we'll come back here and look at the output. But basically, you can, if you look at the output from those 10 files, you'll see different versions, different estimates of pi, and it's just a simple simulation, and each one will have slightly different run times. Mine was going faster here because there wasn't too much congestion, but you can see here that there's quite a bit of congestion on the nodes when we're all running at the same time. Okay, so while that runs, we'll set up kind of what's the next step. Okay, so you have these job array things. What else would you be useful for? So one of the things they're useful for is setting up parameter sweeps. So if you do want to vary the inputs, how would you do it? Well, one way is to use the index, this array index itself, right? So if I open up my job script, I'm going to change my array variable to say 1, 2, 4, excuse me, and 8. And remember, this -b character here was the number of bytes involved in some variable setting. So having an index of 1 byte, 2 bytes, 4 bytes, and 8 bytes kind of makes sense, right? And so again, this is just a simple example. It doesn't really make sense. You'll see with the results, but it's just an example. And I'm going to change this to run the simulation a little faster. So I decrease the number of samples just so the congestion that we're seeing with the first problem is not going to be as big for this one. Okay. Oops. Okay. So that simulation finally finished. Again, you can look at the output. It's not too exciting, but so we've now modified the job script to use non-consecutive array indices, right? And we're actually just using those numbers as an input to one of the variables. So again, if you've made those modifications, you can just submit the job, and you'll see instead of 10 jobs, now we have 4 jobs, and the array index again is non-consecutive here on the total job ID, right? And so this will run. You'll wait probably less than a minute now, hopefully, that we've decreased the sample size. Yeah. So you can kind of see here at the end, this is the command that I'm running here. Oops, let me just clean this up a bit. So we have the output from this parameter sweep across the byte parameter. And I'm going to type this head n2 estimate pi. That was the number of the job ID that I ran. And you'll see, so this is the 1 byte simulation, the 2 byte simulation, the 4 byte, and the 8 byte. And you can see the results aren't really significantly different, and the runtime is basically the same. So whatever I wrote in that code with the byte parameter doesn't seem to really affect the results, at least at this sample level that we ran, right? So that's not too interesting, but it shows you this ability to use non-consecutive array indices here as well, right? To start creating these types of parameter sweeps. Now, what if we wanted to, okay, so the byte parameter wasn't that interesting, so I'm gonna go back here and set this back to 8, just because it didn't really seem to have an effect, but I think 8's the max you can actually run the code with. But what might be more interesting is, well, what if we did a parameter sweep over the number of samples, right? So you can kind of see, how the estimate of pi improves as you increase the number of samples from the code, that the code takes. Right? So it's just another, just instead of sweeping over the byte parameter, now we're sweeping over the sample parameter, right? And if you're reading ahead in the document, you might see that this fails, okay? And so why does this fail? Well, the main reason is, so it's basically, it says there's the job array is invalid. So we've specified it in an invalid way. And the problem was with the index itself, right? So if you sort of look at the Slurm configuration, there are hard limits on the sizes of things. And one of the things that's usually, there's always a limit, but usually there's a limit enforced by your system administrators on your Slurm cluster of the sizes of arrays that you can run, right? And so our array size, the max array size that you can have is 1,000. So, right, in theory, instead of running just 10 jobs, I can run up to 1,000. But this index is really limited to how large it can get, right? And so I can really only run from 1 to 1,000 if I wanted to. That's why this 10,000 sort of causes the job to fail, right? But this is true across the system in general, right? Where there's actually a max job count that the system will even allow users to submit to the scheduler, right? And if you look at the Expanse user guide, I think this might have been covered previously, but there's limits to how many jobs an individual user can submit to every partition, right? Or every, actually it's at the group level, right? So, in this shared partition, the group allocation that we have, we can only submit actually up to 4,096 jobs at any given time, right? If you are working on the system with your research group and you're, say all running in the compute partition, you all can only have up to 32 running jobs at any given time, and a max number queued and submitted at 64, right? That's what these limits are. So there are hard limits on how many jobs you can submit to the scheduler. And so that's one thing you need to keep in mind. On any system, there's going to be a limit to how many jobs you can submit at any given time for your high throughput computing workflow, right? So something to be aware about here, right? Now, in that case, so how do we solve this problem? Well, one thing you can do is use the indexing in a different way, right? And so that's what this next modification is for job arrays here, is we'll go back to just say 1 through 5, but I'm going to use my Slurm task array ID as sort of the variable that, raises 10 to a given power, right? So I start starting to do some shell scripting here where I'm going to declare a variable and export it as a, this is a slightly different notation than just the export command, but this is declaring a variable that's going to be exported to the environment. It's an integer and it's read only. But you can see here I have 10 to ** task array. So this is some simple bash integer math that you can do, right? So I can use the array index as a hook to start scripting things to change the inputs, right? In this case, I'm just doing a direct input, and this is going to be changed to the number of samples. And then I can still run the same sort of parameter sweep that I wanted to, but just doing it a slightly different way without using the direct Slurm array task ID. You can use it as this sort of scoping variable to change some input, that you have. So if you made those modifications, I'm just going to submit them to the scheduler. Definitely going much slower than I was planning. I apologize, but you can see here it's already finished two of the jobs at the low sample counts, and it's just going to run here. It's going to take a little bit longer for those last two, but that's how you can kind of set up parameter sweeps, right? With really hooking onto this, Slurm array task ID, or this, there's going to be some environment variables on any scheduler that use, if you're using job arrays, there's going to be some hook that you can use to help you start scripting your workflows, right? One thing I put in here just for references, if you're curious about like some of the things that I'm doing with the shell scripting, I try to use the Google style guide. So if you're learning shell scripting, it's a nice reference to have of why, like, I put quotes around certain things and maybe why I use declare instead of exports. It's just a nice reference if you're still learning shell scripting. So I'll put that there for just a quick reference. So let's see, there's not too much else interesting here. When the simulation is done, you'll see the output again. We started from, say, 1, 10, 100, 1,000, 10,000 samples. You can kind of see the progression of the estimate getting better. It's, again, not very scientifically interesting, but it's just, a way to get familiar with these mechanics. One other thing you can do with if you're running large job arrays, you can actually throttle the array. So this next example is sort of about using this extra feature where you can sort of say, if I want to run 512 array tasks in a single job, but only have the scheduler schedule 32 at a time. This is one of the options that Slurm provides. So I might skip over this in the interest of time, but you can definitely work through this on your own when you get a chance. I think there was a question. So before I switch to the next section, help desk. Yes, Anna, so this is declaring a variable. The -x is to create and export that variable to the environment. The -i it's making sure that the variable is an integer. If it wasn't an integer value, then it would throw an error, I think, at you. And then the R is to make it read only, so that once I input this integer variable here, right, for the job, it won't, you couldn't modify it later, right? So it's sort of a safety mechanism. If you have a long job script and you're creating this large workflow and you don't want that variable to change later, it's read only. You define it once and it can't get changed later. Right? So that's what the R is for. Again, yeah, I would definitely recommend the Google style guide. I think those descriptions are all in there too. Okay, so that's job arrays, right? So that's one way to start running many versions of the same program. The next topic, I think, is most important, that I will try to go through some of the examples. We only have 15 minutes left, and I will try to touch on some of the other things discussed, but and show you at least a demo of another. But I think job dependencies are very important to understand as well. Right after job arrays, the next thing is sometimes that you want to start creating jobs that are dependent on other jobs, right? So, for example, in this case, what if we wanted to take, our outputs from these other simulations and create some summary statistics of the our estimate of pi, right? I mean, obviously, it's a toy program, but if you wanted to create a job to then summarize the statistics that we've gathered from our simulation here, you could do that with a job dependency, where you create a job that you submit to the scheduler, this dependent job, and you submit it with a job dependency, right? And this job dependency in Slurm has the following format, where you have to specify the type of dependency that you want, and you have to specify like the job ID or IDs that it depends on. So this dependency can depend on, there's a list of different types of dependencies you can have, but the basic one that you start with usually is like after okay. Okay, so this is like you're going to say, I want to run this dependent job after this other job that I have an ID for. And I only want to run it though after I know the first job is okay and is finished, right? So yeah, so we can use this estimate pi example to create our first job dependency, okay? So I'm gonna clean up my directory here a little bit just for clarity. Okay, so I'm just clearing the output, right? So I deleted all my previous simulations because we can run them again, and I'm actually going to speed them up a bit because the last exercise on the previous section was actually to start using this Python version. So I'm just going to copy these modifications and go back to my estimate pi. I'm going to just delete these lines. And paste them there. So essentially what I've done is I've taken the bash version of this pi estimation program out, and I've put in this Python one that does run faster, but might run slower than I'm expecting when we all start running it. But I've used this, the job array, so I'm just going to run 20 simulations, but I've throttled it with only 10 running at any given time. So that's what this notation is here. So I'm going to submit that job and show you what that looks like. Go ahead and open this up for a second. So you see here, I submitted this throttled job array, and that's what this looks like, right? Where I had 20 jobs in my array that I wanted to run now, but I throttled it to only running 10 at a time. And so that's what this job array task limit reason code is. It's basically saying, this is why your job is not running. If you ever wonder what these things in the far right column are from SQ, it's the reason why your job is not running. Okay, so these jobs are pending, and they're pending because they've reached this task array limit, right? I don't need all of, I've throttled this job, and that's what this reason code is. You'll see other ones with like priority, sometimes none. These are, things you can look up in the Slurm documentation. It's a good exercise, I would say, when Nicole was talking about getting help, going to the Slurm documentation before sending in a ticket, like, what does this reason code mean? That's a good thing to like try yourself, right? And if you don't understand still, we can definitely help explain why your job isn't running. Usually it's priority, and people are, that's just because your job is a lower priority than other ones right now. It's that simple. Like, you just have to wait. Okay, so now you can see the first 10 finished. Now the second 10 finished. Again, it's going to get a bunch of output. Now, I've created another example script, batch job script called compute pi stats. And so this is going to be this dependent job example, right? So if you copy this wget command and paste it into your home directory, you'll then have this compute pi stats program or a batch job script. Now, I don't want to get into too much of the details here, but essentially what it does is, like many other things in Slurm, there's once you declare a dependency, there's actually a environment variable that gets created that you can use. So I'm using that Slurm job dependency variable. What I'm doing here is extracting the array job ID that I want. And I'm using that array job ID from my estimate pi outputs to sort of, throw the output into this other program called newplot, which is basically just going to give us a summary of the statistics about the estimates of pi that we had. There's lots of details here. I'll probably have some description of it in the document itself. All you have to know is it's going to, take the output from our estimate pi simulations, and it's going to give us summary statistics. That's kind of the idea. Okay, so what I'm going to do here is, again, I think my previous set of estimates is basically done. So what I'm gonna do here is set up a new batch, right? So I'm gonna sbatch estimate pi again, but this time I'm gonna submit sbatch dependency equals after okay this job ID, and then my estimate, compute pi stats, right? So I resubmitted a new set of estimate pi simulations, Monte Carlo estimates, and then I submitted this job that is dependent upon that job finishing, right? And so what we see here is the compute stats job is not running because it's dependent upon this array of estimate pi jobs that we're waiting on, right? And so now you can see how building job arrays, and if you have complicated sort of high throughput workflows, you can see how these tools, you can start building together these sort of what they would call acyclic directed graphs, right? Where you have all of these sort of, you can have these sort of fanning out like tasks where you take one result, fan it out to a bunch of jobs in an array, then bring it back together, compute some summary statistics in a single job, like this compute array stats. And you can see how you can start building up these complicated workflows based on just job arrays and job dependencies, right? Of course, so these examples are very manual, but it's really just to get you familiar with some of the nuts and bolts of these ideas that you can start using for simple workflows like this. And as I said, every scheduler that you might come across, not just Slurm, should have this kind of tooling built into for you to use, right? So if you have to learn PBS, or I'll talk about HT Condor here briefly because we're almost out of time. But those are the two, sort of tools that I think are most important to starting to do high throughput sort of workflows on the system like Expanse. Now, let me see if there's anything else I want to talk about here before we leave. I think so. I think I just submit the job. You can see the outputs here. Again, the summary statistics you'll see in the outputs. You can check later. Oh yeah, so I do also have, before I just move on for my last 5 minutes to the other 3 topics I haven't quite got to. So we created this first job dependency manually, right? So this run pi workflow is, well, how would you take that and sort of make it a little bit simpler to just, I want to submit a job that sets up the workflow, right? So if you download that run pi workflow job, you can check it out. Again, there's some magic here with grepping and sort of setting things up, but essentially what I'm doing is I'm running sbatch estimate pi, right? I have that array job sitting there. Then that output, I'm filtering the slurm job ID that comes out and sticking it in a variable. And then I just run sbatch again after OK to that job ID. So I kind of just automated that processes of us manually submitting the jobs, right? So that's kind of what this example is for. And I'll just submit it and let it run in the background while I move on. Because I want to try to get out of here on time. Don't want to take up too much extra time. Okay. So again, you can come back here and run these yourselves. Again, you'll just need to remove the reservation if you run them later this week, right? So they should be okay. And hopefully I've sort of documented some of the outputs so you can follow along what was covered here today. The next topic is job bundling. And I do have some links in this section, I think, that you can check out. I finished most of the exercise. I didn't finish all of them. I don't want to really go into this, but the idea, I'll just touch briefly on what the idea of job bundling is. So the idea is, well, in general, many HPC systems actually don't allow you to run a shared job kind of setup like this, right? Many systems, you get scheduled at the whole node level, right? So you have to, if you want to submit a job, you have to use all of the resources on that node for your workflow, right? But if you have one of these high throughput workflows, right, and all we want is to run a bunch of single core jobs, how do you set that up in an efficient way? So that's what job bundling is about. You're essentially setting up this ad hoc scheduling process inside your job, right? You will submit your Slurm job to the queue, but you have to use every single core on that node, right? And so that's what these exercises walk you through. You know, the simplest approach is sort of just backgrounding the process. This first example, you run yourself. There's a key fix though that you have to put this wait command at the end, so you wait for all the processes to run. I'll try to flesh this out a bit more with some more instructions since we don't have time to walk through it together. But there's other ways to set up these running multiple jobs within a single job. That's the whole idea here, right? So I've bundled here 4 of these PyPy simulations in a single batch job script, right? And this is sort of, again, you'll see it gets a little bit more complicated, and you're basically essentially manually scheduling things yourself inside the job, which is fine if that's what you have to do. And there's these other tools like task set and NumaCTL that you can use to do that well. But if you can run job arrays like you do on Expanse, you don't really need to do job bundling usually, right? It's really only if it's a special circumstance where you really do want to pack all of your jobs into one. You know, most use cases I find when I come across users who are doing bundling, it just seems like they're complicating the situation and they don't need to. Because right, if one job fails in your if your Slurm job, like your bundled job fails, all of those individual jobs in there fail, right? But if you use job arrays, only one array task will fail, right? I mean, if it's running on different nodes, and you know, so it's more fault tolerant is what we would say to run using native Slurm job arrays than trying to bundle things yourself. And there's some links in here that you'll see references to that have some stuff already fleshed out more. In particular, there's this kind of little review article from, I think, a recent conference not too long ago about job bundling. And what I'll mention at the end here is really, there's actually I think a long history to job bundling because it sort of has to be done at some level for certain systems. And there's all sorts of sort of ad hoc tools that people have developed over the years. So there's a job bundling tool from TAC called Launcher. There's one from NCSA called Scheduler.x. There's one from NIH called Swarm. So you can probably try these tools out on any system you want if you really do have this job bundling problem. And they're just more complicated. They allow more features though. They're sort of the next step to helping you automate that high throughput workflow, right? And that's, I think, where I'll stop with that. And I'll make two more comments about the last two sections. If you are doing high throughput computing, there are certain systems where you can use what we call preemptible jobs. So that means if your job is able to be interrupted, you might be able to get a discount on running if you run your job in those preemptible queues. So on Expanse, if you look at the user guide, we actually have a preempt and GPU preempt queue. And so if you can write your workflow in such a way to make it resistant to being killed whenever we need your compute resources back, you can get a discount, right? And so for a project where you're really doing this high throughput computing over a long amount of time, this could save you a significant amount of compute time and resources, or increase the amount of science by 20% that you might be able to do, right, if you write your code in such a way. So, and one example I think eventually will end up in this material is, you could think about a way to rewrite these estimate pi codes to be preemptible, right? So that's sort of I guess a homework problem, but you can play around with that. Now I'm just going to take 2 more minutes, maybe 2 minutes to finish up here on this last section. If you are doing high throughput computing, there are actually dedicated sort of high throughput computing native resources out there for you. And so one of them is the Open Science Grid. So if you really do have a high throughput computing workflow, I would highly encourage you to check out their websites. You can also see, just open this up. This is sort of a national resource in the US that sort of combines a bunch of computing clusters across the nation into this sort of virtual cluster. And the idea is basically the Open Science Grid is running a scheduler inside of these clusters that allow you to sort of distribute these high throughput computing jobs all across the country in these different clusters when the resources are free. So it's kind of like this preemptible model, right? So if you can run a preemptible workflow, or many short jobs very quickly on a few compute resources, like maybe a couple cores, a couple gigabytes of memory, this is within a couple hours, this is like the perfect resource for you. And there's all sorts of research communities that use it. It's really it was originally built really for the high energy physics community. So you'll again see, I think IceCube is somewhere listed on here. See it, but there's a bunch of physics communities, a lot of particle physics simulation using this the OSG, and you can get access to it yourself. Basically, almost no questions asked. You just need to work for in the U.S. research community somehow, and submit an abstract, sort of like getting a startup allocation on Exceed, and it all runs on this HT Condor scheduler, which is different from Slurm, but it's a lot of the same sort of concepts you'll see there if you get it. And there's new resources coming online, even at SDSC, that's sort of helping support the OSG community and high throughput computing moving forward. And this is like a new, recently funded NSF program called PATH. And so you can definitely check out these resources. I would encourage you to. Because the path is actually slightly different than the OSG Connect model up here that you'll see if you take a look at the resources. Because I think they actually are going to do allocations through paths, so it's a little different. But definitely check it out. There's some recent information there, and I'll just show you briefly what that looks like. I have access to an OSG submit point. So instead of a SQ, I have a Condor queue, and I can Condor submit. I have my bash pi program here as well. Oh no, did I break it somehow? Oops. Oh, sorry. Yeah, I have a HT Condor submit file, which looks different than the Slurm one, but it's nothing you can't learn how to write yourself. Let's see if you get confused. doing S queues and S batches, and then moving to condors and doing condor queues and condor submits. But basically, I submitted 1,000 jobs, and it'll get sent to clusters wherever, running who knows what version of an Intel processor, an AMD processor. It's sort of, your code needs to be sort of resilient to where it runs. Oops. Hopefully I didn't crash the system. Anyway. Okay, so I'm 5 minutes over time, so I'm going to stop there and take questions.